Today we're going to begin Unit 5, primarily that contains Chapter 8, Chemical Bonding. However, there are some parts from Chapters 9 and 10. What is a chemical bond? There's really no easy definition for what makes a bond, but the definition we will work with is forces. Forces that hold groups of atoms together and make them function as a unit. Let's see, for the image on the right, we've got two hydrogen atoms. The key components you'll note are they have a positive center and then a region of probability around them where that one electron may be. Right now, they're sufficiently far apart to be having no interaction between the two of them. However, as the distance between them becomes smaller and smaller and their electron clouds overlap, then the positively charged region of one will be attracted to the electron cloud of the other, and vice versa. This occurs when they achieve an optimal distance. That is the distance at which the lowest overall energy of the system exists. You can think of it as the most stable state. When the energy of the system is really low, it's really stable and it's not likely to change. Bonds form if the energy of the aggregate, that's the two together, we call that the aggregate, is lower than that of the separated atoms. One thing we're going to have to remember throughout this unit is that when bonds form, it tends to be an exothermic process. Two things are coming together and they are residing at a new energy state that is lower than where they were before. They're more stable than the configuration that they held before, perhaps as independents. And then oppositely, when bonds break, that tends to be endothermic. Energy is required to break a bond. And, think about it. If you look around the world around you, if chemical bonds broke spontaneously with no energy, that's what spontaneously means, things around you would be breaking down right before your eyes. But instead, things actually have a tendency to hold together, and it takes energy to break the molecules apart. We're going to learn a little bit about bond length. A bond's length is the distance between nuclei where an optimal energy is found, right? At this length, attractive energies are maximized and repulsive energies are minimized. Here's a little graphic that kind of helps us understand bond length. If you take a look, we've got internuclear distance, the distance between the two nuclei, and energy, okay? So the bond forms, you can see when the energy is lowest, that's the most stable state. Energy has already been released, and this is the state at which now, as you move these two elements further apart and further apart, they reach a point where their internuclear distance is so great, they're not pulling towards each other. Bonds do not form. And then there is also a distance after which the bond forms that's holds a slightly higher amount of energy. Here's actually an example of some bond lengths for certain bonds. And we want to see if we can see any trends here. We've got a single, double, and triple bond for carbon. And then we've got some other combinations that are in singles, doubles, and triples as well. But let's start by comparing three things that are all made of the exact same atom. They're all carbon-carbon combinations. The bond lengths seem to get shorter and shorter when you have multiple bonds. Okay? So multiple bonds, we want to remember, tends to make shorter bonds. Also, the bond energy. So the energy contained in the bond is highest in multiple bonds than it is in single bonds. So a triple bond energy has a higher energy to break than our double bond or our single bond energy. So let's write down this trend that we've noticed. Multiple bonds are shorter than single bonds and require more energy to break. That's what that means, bond energy. That's the amount of energy required to break it. Doesn't that make sense? It takes more energy to break a triple bond than a double and a single. Now, how bonds come together and what kinds of bonds form is based on something called electronegativity. So we're going to see a little bit about electronegativity to help us make predictions about things like that. So let's start with our definition. Electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. Okay, so this definition implies that the atom's already in a bond, right? So if there's multiple atoms in a bond, whichever one has the strongest pull on those shared atoms, that's the most electronegative. The most electronegative atom in the compound. Different electronegativities in a bond cause unequal sharing, okay? Now, if we have a bond, let's look at this diagram at the top. If the electronegativity difference is 0, then what you have is a covalent bond. When would electronegativity difference be 0? You've got some things bonded together and they're behaving exactly the same. Neither one is pulling stronger than the other. Well, that's going to be called a covalent bond. That's the type. And an example of covalent bond might be hydrogen and hydrogen. They're the same. They're pulling the same. So neither one has a greater electronegativity. For a polar covalent bond, an example would be something like maybe beryllium and oxygen. Now, beryllium has a much lower electronegativity than oxygen. So you're going to have unequal sharing in this bond because the beryllium doesn't pull so strongly on the electrons and the oxygen does. Sometimes to show that, we'll draw a little dash within the middle of the element and then within the middle of the unit, just writing the BE and the O. We'll put the arrow shows the electrons are pulling more towards the oxygen. And then the little plus at the butt of the arrow is saying that, well, what remains is more positive, even though these things are still bound together. When the electronegativity difference is so great, for example, hydrogen fluoride, I mean, these are actually, they've actually transferred electrons and became ions. So they're not even really sharing their electrons. Hydrogen gave up its electron and fluorine took it. And so now these two are just attracted to each other. So they don't have a dipole. They are two separate ions, but they are so strongly attracted to each other that we still call it a bond. And that's kind of a thing that people don't realize. Bonds aren't just sharing electrons or electrons between you. It could just be a super strong attraction as a result of an electron being transferred. So now you should be asking yourself, how am I going to know when one's more electronegative than the other? Here's another periodic trend for you. Electronegativity increases as you go to the right and as you go up the periodic chart, okay? So it increases in this general fashion, and the most electronegative element is fluorine. Fluorine's electronegativity is higher than lithium's. Lithium, that's on the low side, fluorine. Iodine's is lower than fluorine's. Iodine, fluorine. Arrange the following bonds from most to least polar. So just put a little arrow here, most to least polar. So again, if it's polar, it's made of two separate, not just poles, two separate ions. So which one of these bonds will make the most polar? So we're looking for the greatest difference in electronegativity. So I can do carbon is 2.5, fluorine is 4. Oxygen is 3.5, fluorine is 4. Nitrogen is 3, fluorine is 4. So the electronegativity difference here is 1. And I didn't really need to calculate that to figure out the answer, and I hope that you also won't need to. So whether it's a positive or negative number, it really doesn't matter. The difference is 0.5. The difference between these two electronegativities is 1.5. So the greatest electronegativity difference is going to be the most polar. So that's CF has the greatest difference, OF has the least difference, NF has the intermediate difference. So the electronegativity means that fluorine's going to have a stronger pull on the electrons. How much pull does it take to ionize something? That's a good question. We have some standard ranges. So we would say ionic bonds, polar, covalent bonds, and covalent bonds. Electronegativity difference. If the difference is larger than 0.4, then it's no longer just equal sharing. If the difference is between 0.4 and 1.8, we would say it's covalent. And if the difference is um, greater than 1.8, we would say it's ionic. Polar covalent is more of a range that we're defining here, but I would say greater than or equal to. All right, so, and you can kind of rationalize through these next two. They're very similar, where the most electronegative is silicon and fluoride. They must have the greatest difference, all the way to the least. And feel free to check these. I want you to see that you can see those trends for yourself. Now, chlorine. Well, in the middle of covalent and ionic, we have polar. And so we're going to talk a little bit more about bond polarity and then something called dipole moments that happens in a molecule. So a bond dipole refers to unequal charge distribution within a bond. The word here, di, referring to two, and poles referring to opposites. So unequal charge distribution in a bond where elements that are bonded together, such as A and B, if B is more electronegative than A, remember it'll have a stronger pull on the shared electrons, leaving A with somewhat of a positive charge in its region because it has fewer electrons, and B with electrons pulling more towards it. Now here we're looking at just one bond. It happens to make up a simple molecule with two elements, but let's take a look at that bond in a larger context, a dipole moment. This refers to unbalanced charge distribution within a molecule. If we take elements A and B this time, and still make B the most electronegative one, but let's say this time the compound actually has two B's. So it does contain two polar bonds. It has a bond dipole. However, since those polar bonds are pulling exactly opposite one another, then there's no overall negative region of the molecule. There's quite a bit of negative charge here, quite a bit of negative charge here, quite a bit of positive charge here, but there aren't two charged regions. It's not a dipole. So if we kind of put these two ideas together, it's letting us know that you can have a polar bond, but that may not mean that you have a dipole moment within a molecule. We have to sum those bonds together like vectors and see the overall polarity of a molecule. So here, true or false? A molecule that has polar bonds will always be a polar molecule or have a dipole moment. And so that's false, okay? Provide a counter example, where here are several examples where you can see we have a more electronegative element on both sides of this element in the middle, but the way that the charge is distributed throughout the entire molecule, there is not a dipole. There's not two regions of polarity. The same is true here. If you have poles out towards these oxygens, right, because oxygen's more electronegative than most, then these three vectors kind of cancel one another out. They're pulling with equal strength in three equal lateral dimensions, so it kind of cancels one another out. But taking a look over here at water, you have a bond that's pulling towards the oxygen here, and another bond that's pulling towards the oxygen there, leaving these hydrogens slightly positive and the region around the oxygen slightly negative. If you sum all of that together, the whole molecule actually does have a dipole moment, where the oxygen side is more negative and the hydrogen side is more positive. And you'll see us use this lowercase letter d, lowercase Greek letter for D, which is delta. That letter stands for dipole moment. Delta is for dipole moment. So sometimes we will use this symbol with a plus to indicate that there is a positive dipole moment in one region of a molecule and a minus to indicate a negative. These symbols are more used to indicate dipoles in a molecule, not just a bond. For the bond, generally we just use the arrowhead and the plus symbol.